Hi, everyone. So I'll slightly change the topic comparatively to the previous two talks. And instead, I'll focus on generative models that these days are in almost every conversation about machine learning or data science. But instead, I'll try to focus on the usage of generative models for something that has a net positive contribution for society. And that thing is science. And I'll focus on the example of the usage of graph diffusion models for the specific application of digital pathology. So I would like to start by trying to define what is really a generative model. I think that we all agree that a generative model is going to try to generate new data that is similar to our data, but how do we formulate this in a machine learning amenable formulation? And the most widely adopted formulation is that basically we will sample new instances that come from the same underlying distribution from where the samples that we have in our training set came. So basically we have this underlying distribution that generated, by its realizations, generated the samples that we have in our data set, and we want to sample new fresh samples. And the problem is that this distribution is typically unknown, and it can be arbitrarily complex, and we only have access to some of its realizations. So this is clearly an impressively complex problem, which many previous works have been trying to address using deep learning, ranging from variation autoencoders, generative adversarial nets, diffusion models with the first paper in 2015, then normalizing flows, transformers, which are the power units for all these auto-regressive generative model boom that we see nowadays, and finally in 2020, denoising diffusion probabilistic models, so the DPMs, which basically recycle the ideas from the first paper of diffusion with some tweaks. And so basically, as you might be wondering, this talk is not about LLMs. Instead, we'll focus on diffusion models, which, as you might know, were firstly proposed for images and consist of iteratively conspurcating a clean image until we have a fully pure noise on the other side of the trajectory. And the idea is that then we will try to reverse this trajectory, but there's a problem. Typically, this reverse noise model is not tractable. And so the great idea behind diffusion model is that we are going to approximate this reverse noise model with neural nets, in this case parameterized by theta. So basically, in the end, what we have is that diffusion models are encoding this complex distribution where our real data lies, in this case, images of cats, in a fixed way into a simple distribution, a simple Gaussian distribution. And then the neural net will try to, once it's trained, it will be able to map this sample coming from a simple distribution into a sample coming from a complex distribution. And so at the beginning, when diffusion models were firstly proposed, we were obtaining this type of images that were considered satisfactory at the time. But the real boom with diffusion models only came with the DPMs in 2020, where we can clearly see the improvement of quality in the image. And since then, a lot of effort has been imposed in diffusion models, and now we can see really astonishing images that can be even conditioned in almost whatever we want, in this case in text. So given that we have these expressive and quite powerful generative models, why would they be relevant for science? And so to begin with, I would like to go through a statement from two great machine learning researchers, Kingman and Maxwelling, that say that a generative model simulates how the data is generated in the real world. Modeling is understood in almost every science as unveiling this generating process by hypothesizing theories and testing these theories through observations. So as I understand it, we have this world that has an underlying distribution, and by manifestation of reality, the variables that we are measuring are taking given values. And when we develop a generative model, we are bypassing this manifestation of reality. And so what scientists had to do before they would have to come up with these explanatory variables and relate them in some way, so that this generated data would come up and agree with the manifestation of reality. Right now, what we can do is that we just feed our model with this data, and it somehow will learn how to generate it in several conditions. But the assumptions are still the same. Once we have a sufficiently powerful generative model, we will be able to, instead of consulting this expensive oracle that is reality, instead we just run our generative model and we'll get the same data. And so in the end, having generative models is equivalent to having scientific models of reality. And there are several examples in these last few years of how to apply generative AI or machine learning for science, and the applications range from weather prediction to molecular docking or protein folding, where we just condition the generative process to properties of these molecules that are desired, and also in data completion or in compressed representations of the world, such as in GitHub Copilot and ChatGPT, that while you might argue that they are not directly science, at least they are extremely useful for every scientist at this moment. And so also the applications of the generative models also appear in medical contexts, for instance, image reconstruction in sparse data regimes, or for clinical assistance, where doctors are able to interact with a language model that is conditioned on some medical image and might be helpful for clinical analysis and diagnosis. But the medical application that I would like to focus in this presentation is histopathology. And to give you some context, it consists of tissue slide examination under a microscope. So basically from these cells that we see here, specialists can extract somehow relevant patterns for pathology diagnosis and characterization. So for instance, histopathological tests are used for the diagnosis of cancer, of autoimmune diseases, infectious diseases. So it's a really important application here. And more recently, histopathology has gone digital, and these tissue slides are stored as whole slide images, thus amenable to image-based deep learning. And image-based deep learning techniques have been extremely successful in several tasks inside digital pathology, ranging from tissue segmentation, detection, classification, or even for downstream tasks as disease grading or prognosis prediction. The point now is, okay, this is the context of digital pathology, but why would generative models be relevant here? And the point is that there's a shortage of data in this application. Getting new samples is quite time-consuming, requires a lot of work, and is quite costly. They are also under heavy ethical and privacy regulation because these samples come from people, and these people have rights. And then there's also a lack of high-quality annotated samples. So we could use these generative models to get new synthetic data that would address this data scarcity and then could be used in several directions, such as by bypassing these security concerns, because this data that is coming from the generative model does not belong to anyone. It could also be used, for instance, for education, where we could use, where we would have more diverse examples and we could expose pathologists to them, and also for the assessment of these pathologists. And for me, the most interesting application is for deep learning, where we can use this synthetic data for data augmentation, or even to pre-train models that then are fine-tuned in real data. And so, given this context, natural diffusion has been applied with this digital pathology, but the first remark that I should make here is that these whole slide images are huge, and so they have to be patched into small tiles. But once we have these small tiles, we can apply DDPMs to them. And in this work that I'm presenting here, there were 2 tweaks for this DDPM. So basically, they prioritized the morphology in the sense that they weighted the loss function to the first terms of the reverse trajectory, because these are the terms that are learning the high-level features. And then they also conditioned the denoising network on the genotype that they want in the final image. So basically, they would give the type of tissue or the type of disease that they want, and the image would come out accordingly. And so when we compare the results obtained with diffusion against previous approaches, the improvements are clear. However, there are clear limitations of using image deep learning for digital pathology. We can start by the trade-off that I just mentioned before. These whole slide images are huge, and we have to patch them into smaller tiles. And thus, when we are feeding them to downstream models, we are losing the context around these tiles. Moreover, there's also an inefficient modeling of biological relations, because these models are learning relations between pixels, whereas the data from digital pathology is clearly ruled by the interaction between biological entities. And by the same token, there's also a lack of biological interpretability, because pathologists work at the biological entity level, whereas these models are working at the pixel level. So a potential solution for this issue is that you can use entity graphs where nodes are set to biological entities, and we set edges to model the relations. And so being graphs, these are naturally amenable to graph-based deep learning. So once we have this digital pathology patch, we can find one entity graph by first pre-processing with some segmentation and then Voronoi polygons or Delaunay triangulation. And finally, we will have our entity graph, which in this case is a cell graph where we set nodes to edges and we set edges to adjacent cells as a proxy for their interaction. However, this graph formulation for digital pathology data has been extremely successful in the discriminative setting, and there's also room for the generative setting. But imposing diffusion in graphs is especially difficult because graphs are discrete data structures, and the diffusion framework that I've shown you before works for continuous state spaces. Also, GNNs have limited representational power because even though neural nets are universal functional approximators, these GNNs work based on message passing settings, and thus they cannot represent any function over graphs. And also, besides their discreteness, graphs are also sparse, which make the problem even more difficult. And recently, a graph-based diffusion framework has been proposed, Digress, which adapts to the discreteness of graphs by using discrete diffusion. And they address the limited representational power of GNNs by using a GNN, a graph transformer. But when they add as extra inputs features that would not be learned otherwise, like the number of cycles or some spectral features of the graph. And also they make the full diffusion trajectory much sparser by adopting a noise model, which they coin as marginal, which essentially promotes transitions to states that are more common in the data set. So in the end, what we'll have is this chain of graphs instead of images, and where the noise model, instead of being Gaussian noise, is modeled by those transition matrices Q. And to train our graph-based diffusion model under the setting of digress, what we'll do is to have a clean graph and directly conspurcate it to time step t. We should do it in closed form, and it is a very important step in order to have efficient training of diffusion models. And then we pass this noisy graph through the GNN. Okay, this worked through the GNN in order to have the predicted clean graph, and we just impose the cross entropy loss between these two graphs. So basically, the training of the generative model just becomes a classification problem, which is quite convenient. And once we have our GNN trained, we can now sample from this diffusion model. So basically, we first sample a noisy graph from the limit distribution that our noise model imposes, and then we predict a clean graph using the GNN, and we noise it back using this posterior term that basically is a function of the transition matrices that I've shown you before. And so these two steps consist of one reverse step. And if we perform t reverse steps in the end, we will have a new fresh graph. And this is how digress works. But now, the question that I've been interested in the last year is, would this be useful to learn biologically meaningful structures in a biologically meaningful way? And so the structures that I've been trying to generate are called tertiary lymphoid structures, and these are composed by B cells, cell type, clusters, involved by supporting T cells, which is another cell type. And these TLSs are correlated to longer disease-free survival in cancer. So basically, despite being a simple structure, they are biologically meaningful. And also importantly, given one graph, we can compute its TLS content based on previous work. So basically, we can compute this TLS embedding. And so what we'll have here is that we'll build two different data sets, one where we have graphs with high TLS content, where we clearly see one cluster of B cells, the light blue cells, surrounded by dark blue cells, which are the T cells. And then we'll also have a data set with low TLS content, where we have a much more heterogeneous composition. And what we see is that digress is able to approximate the distributions of these two data sets in a biologically meaningful way. So basically, the criteria that we use are these TLS embeddings, and we measure the distances based on several metrics that are used typically for generative models, such as the Wasserstein distance, Jensen-Channel divergence, and so on. So basically, at this point, what we have is a generative model that works for digital pathology in graph format. And so the next idea was to follow the motivation that I've given before and use this diffusion model for data augmentation. And so basically, the setting that we come up with is a small data regime where you have a small data set composed of both graphs with high TLS content and low TLS content. And we will train a classifier to predict exactly this binary label. And we'll perform this training in different magnitude settings. So basically, in one of the settings, we don't do any augmentation. And in the others, we add samples in a given proportion coming from the generative models that I've just shown you in the previous slide. And what we see again is that not performing any augmentation leads to worse performance than when we do any augmentation to the classifier. And in particular, digress is the model which leads to better performance, and it is solely outperformed by augmentation done with real graphs. So basically, these are graphs that are coming from the same distribution of training and test set, and so this would be asymptotically the best that we could have. And also, interestingly, from a given magnitude on, we see that the performance of the classifier when this augmentation is done with synthetic graphs, its performance starts declining. And this can be easily explained by the fact that this classifier in its training is too exposed to synthetic graphs that even though have a slight distribution shift, when the magnitude is too large, it becomes relevant. And so the point is that even though we could improve our capabilities of approximating distributions in graphs, what I think that the next bottleneck for these graph diffusion models is their scaling. So basically, these diffusion models have to make predictions for every pair of nodes. And so this imposes a quadratic dependency on the number of nodes. And to give you some context, the largest graph that I've considered in these data sets is around 100 nodes, whereas in one wall slide image, we can have 1 million cells. So we are clearly 4 orders of magnitude below. And so some of the ideas, I've been trying to tackle this problem recently, and so some of the ideas that I've been wandering around are related to hierarchical generation, where instead of performing the diffusion in the real space of graphs, we'll try to leverage on some graph coarsening technique that allows us to go to a smaller dimensionality latent space of graphs and thus perform the diffusion there. And then once we have our latent new graphs, then map them back to the real space of graphs. And another idea is also to exploit prior knowledge. So basically, we know that these cells that we have in our cell graphs follow some physical and biological rules that we could try to incorporate in our diffusion model. And also, these cell graphs that I've shown you here are by construction planar graphs. And so we could also try to leverage planarity in these generative models. So to conclude, from our work, what we came up with was that using graph-based diffusion models is an extremely relevant to reproduce digital pathology data because these are able to capture higher-order dependencies between cells, and also that the graph diffusion models that we trained are sufficiently powerful to generate sufficiently faithful samples so that then when we use them in augmentation settings, they lead to improved performance. And so this was what I had to tell you, and thank you very much for your attention.
Hello. Thank you very much for your talk. Yeah, I think we have a couple of questions here. Actually, some of them are quite similar, but I want to try to summarize them. Mm-hmm. But let's start for the first one. Ensuring that you are generating synthetic data that corresponds to real cases. But we know that there is the issue of hallucination when generating some of the real cases. How you deal with this, taking into consideration that there is the importance of the solutions that you are building for the augmentation influence actually your model. So
okay. So that's clearly a problem that we might have in generative models, but in some sense, I feel that it's more applicable when we are using this autoregressive setting, or because when we use large language models, hallucination is clearly a problem. But for graphs themselves, they can also give some wrong predictions at some point. But that's why we should. So by nature, these GNNs tend to extrapolate and generalize better, but also that's a clear problem. So we clearly should try to make our distribution approximation to be as faithful as possible to the one that we have in our training set. Of course, there's the issue that we are just we don't really know the distribution. We only have access to some of its realization, so we don't know, and it's typically difficult to characterize tails of distributions and this type of thing. But that's clearly an issue, and that we should keep on improving.
Really quick on the next one, or the combination of the two next ones, is if you're convinced, so if this technique works for generating the new data, it will be possible to tweak it to predict on the regional data sets or the real data sets.
So typically to do predictions in the sense of I have a graph, and instead of generating new graphs, I try to predict a given properties.
Yes.
So typically generating new data is a more complex task than just predicting, because we are modeling the jointly distribution of input and output, whereas when predicting, we are just predicting y given x. So by Bayes' rule, I guess that would be feasible once you have it.
Okay.